Hello everyone, my name is Shizhen Zhao. I'm currently a tenure-track associate professor in Shanghai Jiao Tong University. Today, I'm going to present this paper. To the best of my knowledge, this is the first work that offered theoretical performance guarantee for physical topologies in optical data centers. Nowadays, the most widely adopted data center networks is multi-layered fat tree. This architecture has good scalability and is easy to manage. However, as Ethernet speed keeps increasing, the power consumption of multi-layered networks is also becoming higher and higher. One way to solve this problem is to reduce the number of layers of electrical switches or replace some electrical switches by optical circuit switches. This gives rise to the optical data center. We have a single layer of electrical switches connected to all the servers. These switches are also called top-of-rack switches. These TOR switches are then connected to a layer of OCSs. Using OCSs brings some benefits. First, OCS attains high bandwidth and low power at the same time, and its power consumption does not increase with part speed. Second, the internal structure of an OCS is much simpler. When a packet enters an electrical switch, we need to first pass its header, look at the routing table to decide how to forward this packet, and then enqueue this packet until it is transmitted. This whole process incurs additional delay. In contrast, inside an OCS, there are just 2 layers of mirrors. By rotating these mirrors, we can direct the input light signal to any output port. When a packet enters an OCS, we do not need to perform optical-electrical signal conversion. We do not need to perform packet decoding or encoding. As a result, the packet latency is low. Here is the overall workflow to design optical data centers. First, we need to interconnect the OCSs and the TOR switches. This topology is called physical topology. Then we enter the execution stage. In this stage, the physical topology does not change. To run the network, we need to first get the traffic demand. This can be done either by monitoring the network traffic or by acquiring the traffic pattern from the applications. Based on the traffic pattern, we can compute the optimal OCS configuration to obtain a TOR-level topology. We call this topology as a logical topology. Then we can set up the routing tables for these electrical switches and then start serving traffic. In this work, we focus on the physical topology design problem. Note that at the design stage, we have no knowledge of traffic demand. In the existing literature, when people study optical data center, they do need to propose some physical topologies, mostly using some heuristic ideas. Unfortunately, these physical topologies either scales poorly or have no throughput guarantee. Actually, offering throughput guarantee is very difficult. First, in order to compute the optimal throughput for a given physical topology and a traffic matrix, we need to first compute the OCS configuration, which is in fact a combinatorial optimization problem. We can prove that this problem is NP-complete. Second, since we do not know the traffic pattern at the design stage, in order to offer performance guarantee, we need to enumerate all possible traffic patterns. This is clearly impossible. Here is a contribution of our paper. First, we introduce a new metric to measure the goodness of a given physical topology G. We say a physical topology G has compatibility ratio of beta if for any physical topology G prime and any traffic matrix F, the throughput under G is at least beta times the throughput under G prime. Beta is smaller or equal to 1, and beta equals to 1 means that the physical topology is optimal. Second, we prove that when the number of TOR switches is larger than the number of ports per OCS, no physical topology is optimal. Third, we analyze both the scalability and the compatibility ratios for all the physical topologies used in the existing literature. Specifically, the first physical topology is a uniform bipartite graph. We proved that it has an optimal compatibility ratio, but it can at most support hundreds of TOR switches. The other three topologies can support much larger data centers, but the compatibility ratios are smaller. From now on, we go to the details. Based on the definition of the compatibility ratio, we need to compute throughput values. However, computing throughput values is NP-complete. To solve this challenge, we propose a coupling technique. Given a traffic matrix F, we need to compute OCS configurations first, and then compute throughput based on the resulting logical topology. Given two physical topologies, if these two physical topologies can generate the same set of logical topologies, then these two physical topologies must have the same performance for any traffic pattern. Based on this observation, we can prove that the uniform bipartite graph is optimal. The upper right figure is a uniform bipartite graph. Each TOR switch has L ports, and there are L OCSs in total. There is exactly one bidirectional link between every OCS and every TOR. Since each OCS has R ports, this network architecture supports at most R TOR switches. To prove the optimality of this uniform bipartite graph, we show that this physical topology attains the same performance as the ideal physical topology. In the ideal physical topology, we assume that there is a gigantic OCS, and all the TORs are connected to this gigantic OCS. According to our coupling technique, we only need to prove that every logical topology formed by this ideal physical topology is realizable on top of the uniform topology. Consider an arbitrary logical topology built on top of the ideal physical topology. This topology must satisfy these two constraints. The first one says that the total ingress length of a TOR switch is no larger than L. And the second one says that the total egress length is no larger than L. To realize this logical topology on top of the uniform physical topology with L OCSs, we need to divide X into L subtopologies satisfying these constraints. This constraint says that combining these L topologies, we obtain the logical topology X. These two constraints says that each TOR can at most connect to one ingress port and one egress port in each OCS, because each TOR only has one ingress or egress link connected to each OCS. Actually, this topology decomposition is always feasible. Thus, the uniform bipartite topology attains the same performance as the ideal topology, which means that it is optimal. The feasibility of the topology decomposition is guaranteed by the integer matrix decomposition theorem. I proved it in one of my previous papers. If you are interested, you can refer to that paper. We have shown that the uniform bipartite graph is optimal, but unfortunately, it can at most support hundreds of TOR switches. In practice, large-scale data centers could have thousands or even tens of thousands of TOR switches. Can we design optimal physical topologies for these large-scale data centers? Unfortunately, this theorem says that the compatibility ratio of a physical topology cannot exceed this value. When n is greater than r, this value will be smaller than 1, and thus no physical topology is optimal. If we take the limit of n to infinity, we found that this value converges to 0.5. This indicates that as the number of TORs becomes large, the compatibility ratio cannot exceed 0.5. We briefly describe the intuition behind this result. Suppose we have a physical topology and a permutation pattern. Let's compute the maximum possible number of direct links for 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Take Tor1 to Tor2 for example. In this physical topology, only the first OCS connects to both TOR switches, and thus we can at most create one link from Tor1 to Tor2. Using the same approach, we can get the maximum possible number of direct links is 6. Now, let μgf be the throughput achievable under this physical topology and this permutation traffic pattern. Then, the total amount of traffic injected to the network would be n times mu. This traffic either goes directly from its source to destination or traverse multiple hops. The amount of single hop traffic is upper bounded by the total capacity of the direct links, and the amount of multi-hop traffic is upper bounded by the total capacity of other links divided by 2. From this inequality, we obtain an upper bound of mu. Note that this upper bound depends on MGF. Clearly, the value of MGF depends on the choice of the permutation pattern. We consider the permutation pattern that minimizes MGF for the given physical topology G. We prove that there exists a permutation pattern F star such that MGF star is upper bounded by NLR divided by n-1. Then we could obtain a tighter upper bound for μgf. On the other hand, we can construct the optimal physical topology for any permutation pattern. For example, if Tor1 wants to talk to Tor2, we can always connect the egress links of Tor1 and the ingress links of Tor2 to the same OCS. Similarly, if Tor2 wants to talk to Tor3, we can always connect the egress links of Tor2 and the ingress links of Tor3 to the same OCS, and so on and so forth. We can easily prove that the physical topology obtained this way offers an optimal throughput, and the optimal throughput is L. Combining these two inequalities, the impossibility result is proved. Even though optimal physical topology does not exist for large-scale data centers, we still need to think about how to design a physical topology with good performance. Based on the existing literature, we found 3 approaches to construct large-scale physical topologies. The basic idea is to form EPS groups. In the left figure, we create a uniform mesh among all the TOR switches in the same group. Among different groups, the first TOR switches in different groups connect to the same set of OCSs. The second TOR switches in different groups connect to another set of OCS, and so on and so forth. Note that the maximum number of EPS nodes in each group is on the order of OL. We can enlarge the group size if we use OCSs to interconnect different TOR switches in the same EPS group. See the red figure. In this case, the maximum number of TOR switches becomes R, which is typically 10 times larger than L. The third idea is kind of complicated. To help understand this idea, we first rearrange the second physical topology in this figure. You can see that these TOR switches form a mesh. All the TOR switches in the same row or in the same column connect to the same set of OCSs. We can exchange the rows of the TOR switches and the OCSs and obtain a new topology. In this topology, all the OCSs are arranged in a mesh structure. OCSs in the same row or in the same column connect to the same set of TOR switches. we can still use our coupling technique to analyze the compatibility ratios for these three physical topologies. Here, we show the coupling results between ideal topologies and these three physical topologies. Note that these numbers are L divided by 3 or L over 2 instead of L. The proof strategy is the same as the one we used to prove uniform bipartite topology is optimal, but it's more complicated. If you are interested in the proof, you can refer to our paper. In the end, let me summarize the performance results for all the physical topologies we studied in this paper. The uniform bipartite topology is optimal, but it can only support hundreds of TOR switches. The EPS group and the OCS mesh topology could support thousands of TOR switches, but their compatibility ratios reduces to 0.3 to 0.4. The EPS mesh topology could support tens of thousands of TOR switches, while its compatibility ratio is the smallest. To conclude, we define a new metric to evaluate the goodness of physical topologies for optical circuit switch data centers. We show that the widely used uniform bipartite topology is optimal, but scales poorly. We prove that it is impossible to construct a physical topology with beta equal to 1 when the number of TORs is greater or equal to the number of pores per OCS. We explore three different physical topology designs and analyze their scalabilities and compatibility ratios. Our results are useful for network planning at the design stage. Thanks.